In today's video, we're testing if diamonds really are forever. What happens if we try to burn one? Previously on this channel, we've showed you how to make liquid oxygen by taking liquid nitrogen, putting it in an insulating container, and letting it just evaporate off.
Once the liquid nitrogen has boiled off, you're left with a very small amount of liquid oxygen, which is a very cold, very pale blue substance.
We should get a little bit in each of these 8 cups, and we already set these up to start letting the liquid nitrogen boil away because it takes at least an hour to do. And we've gotten it to the point where it's boiled down most of the way, but we've still got at least 30% left, I think. Hopefully over the next 15-20 minutes that will boil off and we'll get that pale blue liquid Callie was explaining about. That should be liquid oxygen, and we should be able to just combine that all into 1 cup once we're done and hopefully do some cool experiments with that and our 3 forms of carbon that we have.
Pencil graphite, charcoal, and diamonds.
All 3 of these types of carbon are things that we see and use in our regular days, and they all have pretty different properties. Charcoal, of course, comes from burning wood in a low oxygen environment, and graphite and diamond are both naturally occurring forms of carbon that are mined from the ground.
So while diamonds are still, as far as we know, the hardest substance, they're actually weaker than graphite in one way. The atomical structure of a diamond is formed in a 3-dimensional lattice, whereas a graphite is actually formed with tightly bonded sheets. Now, it's actually kind of interesting because at a chemical level, graphite is stronger.
However, in practical use and size, in a way that we're going to run into, you can crumble graphite with your fingers, you can crush charcoal with your hands. With diamonds, you're going to need something stronger. I don't think I could crunch a diamond no matter how hard I tried.
I mean, you could try. It'd be entertaining for all of us.
It's just not going to go anywhere. So, once our liquid oxygen is finished forming, we can start doing experiments with our 3 forms of carbon and that liquid oxygen to see how they react.
Here's the basic idea. We have 3 different types of carbon, and we want to see what happens if we burn them in liquid oxygen.
All right, guys, time for a quick update. We had our cups full of liquid nitrogen trying to extract oxygen out of the air, and how much did we get out of that, Callie?
That would be none.
0, like not even a drip down at the bottom, absolutely none out of that. So, we decided to scale up to a slightly more industrial oxygen farming technique, and we brought in our friend Alexander to show us how best to do that. Alexander, tell us just a little bit about your experience in this field.
Well, I am currently studying engineering at the University of Utah, and sometimes we do demonstrations in which we might need liquid oxygen. And so the method that we use is we use an industrial oxygen tank and then a little bit of liquid nitrogen. It turns out that nitrogen boils at about 77 Kelvin and oxygen boils at about 90 Kelvin, which means we can use liquid nitrogen to condense oxygen gas and form liquid oxygen.
So right here we've got, this is just a coil of copper. It was like 10 bucks at the hardware store. We then wrapped it around a piece of PVC pipe, being very careful not to kink it anywhere so there is still smooth flow all the way down. So it comes in through this hose here and then travels all the way down to the bottom coil here.
And this part is submerged in the liquid nitrogen.
Yes.
Correct.
That's what's freezing the oxygen.
Yeah.
Awesome.
And then this comes up, back, and hooks, and so we'll have liquid nitrogen in this. This gets submerged down into the liquid nitrogen, and you can see it's just got a little fountain spout, and we're just going to pour that right into our styrofoam cup.
So basically the idea is oxygen gas comes in here, this entire length of copper tubing is going to cool it down about 300 Kelvin, and then right at the bottom it's going to have the right temperature that it will condense into a liquid, and the back pressure from the oxygen gas will pour it out.
We'll get a nice little fountain of very pale blue liquid pouring down into our styrofoam cup, and that's when we can really start the fun. So let's pour some liquid nitrogen off and then turn on our oxygen tank and get this fountain going. Most of the bubbling has settled down. I mean, there's still bubbles coming out of it, but it's settled down to the point where it's not like exploding all over, which means our copper has now been cooled down by quite a bit.
All right, so we're going to start the flow of oxygen, and then we should start to see in like 10 seconds a nice pale blue liquid coming out of the spout.
I'm just clearing the line, I think.
Yep. So right now we're cooling the oxygen down about 300 Kelvin, and then as soon as it gets to that temperature and we get a sufficient amount of it, it will start pouring out into the cup here.
Awesome.
Okay, so we can start to see little bits of liquid oxygen.
Oh my gosh.
And now we're starting to get a more consistent flow. You can see as the oxygen makes contact with the copper here, the frost recedes back because it's actively cooling it again. So 1 milliliter of liquid oxygen expands to about 860 milliliters of oxygen gas at room temperature. What you're seeing here, once we've filled up this cup, is really quite a significant quantity of oxygen gas.
A quarter teaspoon of it would provide enough oxygen gas to fill like a 2-liter bottle, or a 1-liter bottle.
Yeah.
So check this out. We now have a big old cup full of liquid oxygen. It's a nice pale blue shade. If I stick my finger in it real quick, it's gonna freeze my glove, pretty much the same way liquid nitrogen does.
It's also significantly more dangerous than liquid nitrogen. So liquid nitrogen, basically the worst it can do is freeze your skin and give you cryogenic burns. Liquid oxygen can do that as well, but it can also help things become extremely flammable. So oxygen gas itself is not flammable. That's a pretty common misconception. Things like propane, hydrogen, those are flammable. Oxygen gas is important in sustaining fire though. And right here we have a cup of very, very concentrated oxygen. The oxygen in the air around us is about 21%, and obviously the air isn't very dense. This is about as dense as water, and it is 100% oxygen, which means that it will allow us to make things that aren't normally considered very flammable burn extremely well.
We've got some liquid nitrogen here. We've got a clear cup, and I think we want to use the clear cup to do this in so we can see things a little bit better. But we don't want to lose too much of our liquid oxygen, so we're going to use the nitrogen to cool this down before we put the liquid oxygen into the cup.
Oh, it's so pretty.
Yep, it's a beautiful pale blue color because it absorbs all of the red wavelengths from the atmosphere.
Is that?
Wow.
I did not know that.
Yeah, so the quantum notation for that is triplet sigma Gerada oxygen molecule goes with added to the product of Planck's constant and the wavelength that you're going to absorb, then goes to a singlet delta Gerada oxygen molecule.
You lost me at triple singlet stigmata. This is charcoal. Charcoal is almost entirely carbon. It's not going to be 100% pure. There's going to be residue left from the wood and gas and stuff like that, but it's mostly carbon. So what we're going to do is we're going to get this burning and then drop that down into our pure liquid oxygen. And it's not going to explode.
No, it shouldn't explode. The oxygen is going to be stoichiometrically in a very high excess, so it should burn very readily and very brightly, but it shouldn't explode.
All right, here goes.
We're trusting you, Alexander.
Just gonna hit this little tiny piece of charcoal with a blowtorch. Here goes.
Yep, so you can see, even though it's currently sitting in a cryogenic liquid, it is still burning very, very brightly, and that's because there's lots and lots of heat being formed, and that charcoal is currently being converted and has now been all converted into carbon dioxide gas.
That's cool. And there's no residue. There's nothing left.
Since it's acting in a pure oxygen environment, there's going to be nothing left but gas.
That's amazing.
Yeah.
By the way, the super awesome slow-mo footage we've got today is courtesy of Kuma Films. This is amazing. So
look at the sparks.
Even just right as it was falling in, like when it was at the top of the cup, first falling in for the first time, it was pretty dull. By the time it reached the surface, it was already glowing brighter. So you can see it's just in the higher oxygen environment. It hasn't even hit the liquid yet, and then it does hit the liquid and just goes crazy.
That is gorgeous. The bounce, yeah, and then all the sparks that come off.
It's like a personal fireworks show.
It really is. Fireworks in a cup.
Next up, we have our slightly more ordered form of carbon. This is graphite that's been pressed together into the shape of a pencil core. We broke a piece out. We're going to try and burn this, drop it into the liquid oxygen, and see if there's anything different about it than the charcoal.
It's not really doing as much as I thought.
Maybe it wasn't hot enough.
Well, it's bouncing around.
It's not stopping though.
No.
It's still reacting.
But only the part that's outside. Yeah.
Yeah.
It went out.
We didn't get any reaction out of the graphite, and it's possible that our torch wasn't hot enough. It's possible that the configuration of graphite we pulled out of a pencil is maybe a little bit the wrong formula, but there is one more type of carbon that we want to try.
Diamond.
That's right. So, we have some diamond... Callie, where's our diamonds?
Okay, look. I believe total I was wearing 1/8 of a carat.
1/8 of a carat of very low grade, but still diamond.
Still counts.
That's glowing pretty nicely.
Glowing orange, as are the tip of my
Beautiful.
forceps.
What happened to our last diamond, Nate? What'd you do to it?
I burned it up. So I was using these forceps, and they were very cheap, and my torch actually started just melting them. So I was having a really hard time holding onto the diamond, and I kept dropping it. And then one of the times I dropped it, there was just nothing left to pick back up.
So here you go.
I'll try not to burn this one up until I drop it into the liquid oxygen, at which point I hope it burns up spectacularly.
Cool, 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 cool. Already cool. Awesome. Oh my
Yeah,
gosh.
there we go.
Woo!
It took some doing, but it started and actually burnt.
Shine bright like a diamond.
It's new meaning to that term. That's so much cooler of an ending than most diamonds are going to get.
Can you destroy diamonds?
You can destroy diamonds.
Innumerably many ways, but this is probably the most fun.
We're just going to show. I'm not actually going to drop this in. I'm just going to hold it. Oh, yeah.
Just right over the top.
Just that oxygen-rich environment. That's just charcoal burning at its fullest. This has been really cool. Alexander, thank you for your expertise.
Kuma Films, thank you so much for the amazing slow-mo shots that we got today.
Oh, it's amazing.
Beautiful.
Amazing.
Guys, Kuma Films, they've got really cool stuff on their channel. Go check that out.